we were able to remedy the problem. Long story short, the problem was that the versions of SciPy and scikit-learn were incompatible, which speaks to the following notion. Upgrading is not always a good thing. Because when you have a complicated code base like scikit-learn and SciPy, sometimes you write one piece of code not knowing how it affects something else. In this case, the most recently upgraded versions of SciPy and scikit-learn don't play well together in the tree module. I don't know if they know that. So I'll probably submit a ticket to them later tonight. So they do know that, because that's really important for data scientists. To remedy it today, here's what we have to do. In your terminal, you will type in two things. The first thing you will do is the following line of code. Conda install scikit-learn equals 0.16.0. If you run this, it will try to find that specific version of scikit-learn. It will find it, and it will say proceed, yes or no. I'm going to do it with you. Yes. And then it'll do the following, done. So the top line, this conda install scikit-learn, that's the one thing you have to type in. And then it'll ask Y or N, yes or no, hit Y, enter, and then you'll see a bunch of pound signs. There's their progress bar, and it'll be done. Conda install scikit-learn equals 0.16.0. The next line of code you will write is the following. Conda install scipy equals 0.15.1. It'll say proceed, yes or no, and then more pound signs. So here I'm highlighting the second thing. There's only two lines of code. Everything else is just output. First, it has to be in this order. Scikit-learn has to come first, and then you do the scipy one. Because what happens is when you upgrade scikit-learn, it also updates scipy. But it upgrades to the bad version. So then we override it by saying, no, I want this version of scipy instead. So we want 16.0 of scikit-learn and 15.1 of scipy. I'm sorry. I'm really sorry. This was confusing. It's my fault. I should have checked. I don't even know how I would have checked, but I should have checked somehow. Should have called all of you to run the code beforehand to see if it works. So please, when you run this, the last thing you have to do is in your spider, on the top right, you'll see a button next to the red. Hit restart kernel. Restart kernel, hit yes. It'll be as if you're opening it for the first time. Go ahead and run the beginning lines of 13 trees once it connects. Once it connects, okay, once it connects, run it, and it should work. Like magic. Black magic. I want to see, can you try it?
I will try. Will you do it? Yep.
Did it work? Yes?
Yep, I'm good.
It all imported? It all imported? Is anyone still getting an error when this happens? I'm getting no hands. You're getting errors?
Well, it's stuff, like one the whole code.
What?
It's run out of correctly packaged.
Yay, it worked.
Did you design it already? Restart the kernel. Anyone else getting errors? Someone will be with you shortly if you are still getting errors. If you don't raise your hand, I will assume you are good to go and I will keep going. Okay, thank you for raising your hands now. Yes. So what? Oh, I'm sorry. I thought you said something completely different. First line of code is at the top. And they said, can I speak generally? It's like, sure. Conda, here are the two lines of code. You're still getting an error?
No. How do you restart your kernel?
Good question. In Spider, in the top right of Spider, next to the red button is this button. Looks like a document, and hit restart kernel. You're still getting there?
I don't know why I can't find the file.
If you restarted Spider entirely, you might need to rechange your working directory. But that's just hitting this button and going to the file, into the code. Anyone? Yeah.
Sorry, where did we leave off? Where are we all trying to...
Oh, yeah, so I'll make sure. Can everyone import this? If you can import this, we're good to go. If you cannot import this, please raise your hand. Someone will be with you shortly. Okay, we left off here. Line 170 is blank space. If you go all the way up and just run all of that, warnings, done. We're now up to date. So starting when it says let's get KNN and naive Bayes to join the party, that's the last thing I said, which is strange now that I think about it and say it out loud. But it's the last thing I said to you before all hell broke loose. So if you run everything before this, it should only take a couple of seconds, up to 10 seconds. You should be completely up to date. Am I getting, this does not work, please raise your hand and someone will be with you shortly. But if you are not raising your hand, I will actually assume that you were able to run all 170 lines of code in one instant. Great. Welcome back to Data Science San Francisco. My name is Alan Osborne. Thank you for sticking around. We left off on an exercise. Let me back up first. So, the last thing we did was that I imported a logistic regression. I made a logistic regression, a base one. I made a base C tree, didn't fit it to anything. Used the cross-val score 10 times to get an ROC for both logistic regression and decision trees. And we found that logistic regression actually had the best ROC AUC. The exercise, what I actually do want you to do now, is to import naive Bayes and KNN to get their cross-val scores with ROC AUC. So that you should end up with 4 numbers, which should show you in general which model is doing better at predicting this response. So you're going to import KNN naive Bayes, instantiate a blank one, and then use up your cross-val score. All in all, that should be 6 more lines of code. 1, 2, 3, 4, yeah, 6. 6 lines of code. Well, 8 if you count printing the 2 numbers.
1 and 1. You just said run this code.
So you want to run with the, oh yeah, exactly. So you want to see both of them or print.
Well, I had done this from the previous time.
So if you run, here's the difference. You run the properties and you'll just keep the last one. So here's the NB. Go ahead and choose how many Ks you want for your KNN. I did 5 below if you want to mimic mine, but you have to choose how many Ks you need for your KNN. Crisis averted.
I think that's where you, let's say, you don't have support in the scaling
Log reg is 5. Only difference here is the log reg versus tree. So you actually only know the difference.
Now, my CD was 10.
And you measure how low the candle is.
version.
So why is it better?
So you have to update
Okay, what was your name base?
So that way.
just to find out
Let's go. For the science fair. You said what's what do you put in that? What was your log?
C.
Well, I was already.
And then with practice, we'll run like which types of
yeah, so you are going to you didn't start the contact we didn't get that one
For log reg.
That's what we do.
Yeah.
So what do you guys get?
So where is K?
So you bring in multinomial NB.
What was your
I'll make an NB. I'll import k-neighbors classifier. I'll make a new k-neighbors classifier with n neighbors equals 5. And then I'll have the same exact code as before, literally the same words. Just instead of log reg and C tree, it's NB and KNN. And when I run it for NB, I get 0.8099, and for my KNN, I get 0.8187. What we just did was we used 4 different classification models, fit them all to the same data using a 10-fold cross-validation in order to minimize the variance that's inherent. What is the output? Can someone interpret 0.81, 0.8099, 0.801 for the tree, 0.85 for the log reg? Can someone tell me what those numbers are telling me? What does it seem? Say it. Is. It seems that across all thresholds, if you don't set a specific threshold or tune parameters, remember, we're not tuning any parameters. Max depth of the tree is still 2. We use 5 neighbors. If you set all those the same, it looks like log reg is the best. Does that mean that logistic regression is the best model for this case? Not necessarily. Maybe a tree with 10 depth would be better. But we wouldn't know until we tried. We just wouldn't know until we tried. So far, logistic regression is winning. But let's fine-tune the tree to see if we can make it better than logistic regression. Because if you remember, what's the quote-unquote nice thing about logistic regression?
Stable.
It's very stable, yes, very low variance. What else? What other parameters? You remember? Same thing as linear. Linear and logistic regression have something in common that make it very easy to use. What is it? The what?
2 variables.
It's 2 variables. I think 2 variables.
It's just 2.
You're on my track. Variable might not be the best word for it. How about parameters? So remember in K and N, what is a parameter that we usually change to see if it's better? What parameter do we try to change? K, right? K, how many neighbors? That's how the thing. You can also change the metric, Minkowski, you can also change this and that, but K is generally the thing that we change. Remember the grid search? Logistic and linear, you don't tune parameters. You pretty much don't tune them. There are no parameters to tune. If you notice, we did not do a grid search with linear regression or logistic regression because there really is nothing to change. Unless, and we said this last time, unless there is you're doing a very more complicated form of logistic regression or linear regression. In a basic linear and logistic regression, there's no parameters to tune. In trees and what about naive Bayes? In naive Bayes, can you change anything? Yeah, can't. There are parameters you can tune in naive Bayes. There's also parameters you can tune in trees, one of which is max depth. So let's fine tune our parameters. For that, I will use grid search. Remember, does someone want to explain what grid search does? What does grid search do?
Find the best depth.
How? You're right. You're absolutely right. It will find not just best depth, but it will find the best combination of parameters. How does it do it?
Gives each scenario.
It tries each one. Exactly. Exactly. It tries each one. It tries each combination of parameters and will tell you the best one. Based on what? Aaron, based on what? Sorry?
I'm sorry, I'm doing something else. Sorry.
So, do you mind if I ask you the question then?
Sure.
So, when I am doing grid search, it will try all possible combinations of parameters. And then it will tell me the best. How does it know what the best is? You tell it. You're exactly. So you have to tell it. Judge on accuracy. Judge on ROC AUC. Judge on root mean squared or mean squared error. So you tell it how you want it to judge. So without grid search, this is what we would do. We would say, okay, fine, try max depth equals tree, and then do a mean of the cross valve for the RUC. 0.837. That's a little bit better than the 0.80 we had before. Fine, let's try it with 10. Let's try it with 10. 0.81. Uh-oh. What happened? The error went down. So to put that in a graph, and there's a graph coming up, but before I show you the actual big graph, to put that in a graph, if I have on the x-axis, if I have depth and my ROC, at a depth of 2, I had an accuracy of 0.80. When I had a depth of, I tried 3, I had 0.84, and then when I had 10, I had 0.81 again. What happened? Why did adding complexity make it even better? This goes back all the way to day 2 or 3 of class. What? Oops. 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 We're overfitting. Uh-oh. Show me the graph. Remember this? As we add model complexity, look at the error. The error will hit a minimum at a certain model complexity, but then as you get more complicated, it starts to overfit, it starts to break down, and error shoots back up. So an ROC is essentially the inverse. As error goes down, your ROC will go up. So in this case, as I added model complexity, my ROC went up, it got better. And then I got to a certain threshold of complexity, and then I started going down again. So grid search will help us find where did it actually do that? So here, I will make a decision tree with random state 1 so we get the same numbers. I will try from 1 to 20. So a depth of 1, what does the depth of 1 mean? You have one choice, and what will it probably choose? Gender. You have one choice, as opposed to 20. You are allowed to go down this tree 20 times. So for max depth, it has from 1 to 20. I will give it a cross val of 5, and I want to score on ROC. Fit. It is now actually running 20 different trees. Here are the mean scores, and I will plot them. This is a graph that is so common. This is a graph of ROC versus complexity, max depth. In pretty much every single situation in machine learning, almost 99% of the time, as you add model complexity, your model will get better up to a certain point. At a certain point, your model will start to overfit and break down and deteriorate. So it's all about finding that red circle. Using grid search, it will see 5. A max depth of 5 appears to be good. Why do you think it breaks down after 5? I mean, think about it. It's asking 20 questions. If you allow it to answer 20 questions, it just doesn't know where to stop. It just keeps asking itself really annoying, redundant questions like, are you over 28, 29, 30, 31, 32? I missed everything. Because it thinks I have more room to ask questions. I can ask more questions. Let me keep going and see if it's any better. But when you say stop at 5, that says, okay, apparently that's maximum stopping criteria. So it's all about bias variance trade-off. As I add model complexity, my bias is decreasing. Bias is decreasing, which means my ROC is getting better. But after a certain point, it breaks down. From our grid search, we can get our best B. So now I'm going to try my best versus that log reg. The best one that came out of my grid search, I'm going to compare that to the base log, the base logistic regression. So cross-val score, 0.847, and my log reg, 0.853. It's still doing better. Son of a bitch. Let's try something else. Exercise for you guys. Take 5 minutes. Do a grid search with 3 parameters. Max depth from 1 to 20 like before. Criterion. Criterion is when you tell it either Gini or entropy. Default is Gini. But your criterion range will not be like a range 0 to 20. It will be a list of Gini and entropy. Max features 1 to 5. What is max features? Like max depth, you're limiting the number of questions it's allowed to ask. Max features is I'm limiting you in the number of features you're allowed to even look at. So I'm giving it 6, but I'm saying you only get to choose either 1 to 5. So maybe you'll only choose age and sex if you have 2. Or if you have 3, maybe you'll choose age, sex, and class. So try to make a grid search with 3 different parameters. Use the code up here to model it. It's pretty much all the same except for these 2 lines. You'll have more than just max depth equals. You'll have criterion equals. Max features equals. So try to use a grid search for these 3. We'll say 5 minutes to do that. Also, don't forget the person next to you that can help.
We're losing each other.
That's cool. So I got my depth range is the same from 1 to 20. My criterion range is now a list. Just two things, Gini or entropy. My max features is just 1 to 5. Put them together in the dictionary. Max depth equals depth range. Criterion equals criterion range. Max features equals max feature range. Notice the keys are exactly the same name as the features in the list, in the decision tree. Criterion and max depth, all the same keys. So I'll do that. We'll run that code first. So if we look at ParamGrid, it's a dictionary. It's all just a dictionary. It just holds the possible values that I want it to choose from. So for criterion, I want it to choose from either Gini or entropy. In max depth, I have 1, 2, 3, 4, 5, all the way to 19. And then for max features, I have 1, 2, 3, 4. These are just all the things that I want to try every single possible combination. How many combinations are there? How many combinations are there between 2 criterias, 19 max depths, and 4 max features? Say it again? 76 times 2. 19 here, times 4, 76, times 2 criteria. For Gini, there are 76. For entropy, there are 76. So how many total is that? 152. So it's going to make 152 decision trees. Not only that, it's going to make 152 decision trees. For each one, it's going to train it 5 times to do a cross-validation of 5 times. So in total, it's going to fit 670 different machine learning models. 1, 2, 3. I didn't use the time it. I forgot. I was going to do it a lot for a lot of different things, and I didn't want to wait. Now I'm trying to kill time because it's fitting 670 different machine learning models. And now it's done. I can check out the mean scores, of which there are a few. I would graph it, but what? Say it again. Well, there's 4 dimensions. I have the axis of criterion, Gini entropy, which is an axis of 2, but it's still an axis. I have the axis of max depth, which is 1 to 19. I have the axis of max feature, which is 1 to 4, and then I have the axis of the response. There's four different axes here that I can't just easily plot. But I can get the best one. Let's now try that best one versus logistic regression. I'm feeling good about this one. 0.8544, 0.8539. Barely beat logistic regression, but it beat it. And then I take that, logistic regression. Pew pew! Pew 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 is a laser gun. It's a what? It's a technical term for yeah. Decision trees, also like other classification models, can also be used for regression. You might not know this, but you can use K-neighbors classifier as a regression model. You can use logistic regression if you want as a regression model. It's not a good idea. But decision trees can also be used as regression models. We're almost done with this code. Remember drinks? Yeah. Drinks. 6 columns. We got continent, total liters of pure alcohol, country, beer servings, spirit servings, wine servings. We're familiar with this data set. So the first thing I'm going to do is I'm going to, for each of the continents, I'm going to make a column. For Asia, I want to make a column called Asia. For North America, I'm going to make a column called North America. And spice it for all the continents. Each one of them is going to be a bunch of trues and falses. Each row is going to have Africa, false. Europe, false. North America, true. South America, false. Asia, false. Australia, you get it. I'm going to make a dummy column for each one. So what does that look like? Now there's 12 columns. Because I've just added 6 new columns. See, notice how South America is now a bunch of falses and trues. It's true if that country is in South America, false if it's not. For Oceania, same thing. False if it's not in Oceania, true if it is. Why am I doing this? Because that's how I'm going to convert it to numerical variables. Because Oceania, North America, South America, those aren't numbers. I can't do quantitative operations on that. But if I turn them into dummy variables, which are true and false, or 0 or 1, I can now perform math. So now I can compare across different models that use quantitative variables. I'm going to delete continent from drinks. I'm going to delete country from drinks. I'm going to delete total liters of pure alcohol because it's kind of unfair because that's a combination of the variables that I have and what I want. And I'm going to try to predict wine servings based on everything else. So to kind of take a look at this, X train now has 8 columns. Show me the data frame. Beer servings, spirit servings, Asia, North America, Europe, Africa, South America, Oceania. Those are now my features. Remember, these are actually interpreted as 0s and 1s, as trues and falses. So they're all actually numeric columns. And I'm going to try to predict wine servings. So I will make tree.decision-tree regressor instead of decision-tree classifier. It's that easy. Decision-tree regressor. And I will treat it as if it were any other regression model. I will fit to the train, predict the test, use a cross-val score to get my root mean squared errors. So remember here, the only difference that I use in the cross-val score is that now I'm telling it, instead of ROC underscore AUC or accuracy, I'm telling it mean squared error. Arthur's changed the scoring string to be mean squared error. Some of you may have noticed that sometimes when this works, they'll give you negative numbers. I don't know why it does that. And I challenge anyone to find out, and please tell me. I don't know why it does that. Sometimes it gives you negative numbers. Do you guys happen to know, Lean, Patrick, or Ramesh, why a cross-val score gives me negative numbers when I do mean squared error? I don't actually know why it does that. To be quite honest, I have no idea. But to remedy it manually, I just say it's the negative. So now they're all positive. I will take the square root of each one. And then now I have 10 different root mean squared errors. I'll average them together to get 77. Is that good? Can someone interpret the root mean squared error a little bit for me? The fact that it's 77, what can you say about that? It's a regression. So root mean squared error being 77 means what? What are we trying to predict? What? Our y, our response, is wine servings, which is a continuous number. So we are using regression to try to predict a continuous number, wine servings, based on beer servings, spirit servings, and the 6 other continental variables: Africa, Asia, Europe, trues and falses. So our response is what? You try this time. Our response is wine servings, which is a continuous number. Wine servings, wine servings, wine servings. Desiree, what's the response? No one's listening. Yes, you're right. Wine servings. It's continuous, therefore we're doing a regression problem. So, a root mean squared error is a way of assessing how wrong I am. So can someone try to interpret the root mean squared error now? 77. What does that mean? Yes, that's right.
That your answer could be off by 77
On average, you can expect my prediction to be off by 77 wine servings. That sounds big, but is it big? Because some of these countries have a wine serving of 500 something. So when you say 77, that's not so many wine servings in a year. So in a year, I'm all generally off by 77 wine servings in a year. You always have to keep in mind the scope of things. Also, the average of wine serving, the average wine serving is only 49. The average wine serving is only in the world. The average wine serving per person per year is 49. Do you remember why this number is very, very low? A lot of countries have 0 reported wine servings, which drives down our mean a lot. We can look at the feature importances. In the regression as well as the classification tree, we still have feature importances because it still uses Gini or entropy to calculate the splits. So this interpretability still exists. So when predicting wine servings, it says beer servings was the most important, followed by whether or not they were in Europe, followed by spirit, and then so far and so forth. I think this is interesting. What are we trying to predict? Yeah, we're trying to predict wine servings. Doesn't it, quote unquote, make sense that whether or not the country was in Europe was actually the second most important decision? That's how easy it is to interpret this. Because you're all laughing because it's funny, because it's kind of true. We've never been able to quantify this so easily. When predicting wine servings, it appears that how much a country drinks beer, and also whether or not that country was in Europe, were the 2 biggest decisions to make, to figure it out. Everything else wasn't so important. Being in North America apparently is not very important when you're trying to decide how much wine you drink. Doesn't matter. So whether or not you were in Europe, that was a big difference. Because people in Europe like wine. A drawback to the feature importances, because now you're all like, F everything else, I'm using decision tree because it's great. Well, I have to tell you, one big drawback is, even if your model, this is assuming that I can predict wine servings well. This says nothing to accuracy, root mean squared error. This doesn't say anything about how well your model is doing to predict. All this is telling you is which features it used the most. So really, take this with a grain of salt. That grain of salt being your other metrics like accuracy and sensitivity and specificity. The ones that actually quantify how well you are doing. This is not telling you how well your model is doing. This is only telling you these are the features that I think are the most important. That being said, these will always add up to 100. No matter what. No matter what, these will always add up to 100. Even if your root mean squared error is 1,000, these will still add up to 100. So you can't just take this as your tell-all, end-all metric. You'll never be able to do that for one specific metric. This is a fantastically simple way of interpreting your features. Given that your error metrics are also looking good. You know, my root mean squared error is 77, that's not so bad. That means I can trust these feature affordances. You can still use this to cut down on features. So what you could do is say, okay, then screw these, use these top 3, and then make a new decision tree and see if that works. So you can use it to fine-tune your features. But please, please, please do not only use this as your metric for classification decision trees. Make sense? But it is still cool, right, with the Europe? Well, I thought it was interesting. All right. That's all I have for this Python file. For the remaining of class, oh, I forgot. I don't know if you noticed I have Tinder.py up here. In the fun folder, I wrote a little Tinder API scraper. I know. I found the Tinder API. So if you want to try it out with your own Facebook token, there's ways of getting your own Facebook token. You can plug it in here. And with your own, that's my Facebook ID. Whoops. And you can go on Tinder and do stuff. I'll post a link to the documentation. But it's, for the remainder of class, there is a lab. The lab focuses on UN data, which looks like this. Excel. It's fine. Calm down. For each country, I believe this is 2013 or 2014 data. For each country, it tells you the life expectancy for males, for females, for the infant mortality rate, and the GDP per capita. Can someone explain to me why infant mortality rate is sometimes above 100? It's out of, I think, 1,000. It's not out of 100. It's not out of 100. I was under the impression that it was out of 1,000. I want to make sure because that's really important. ... Google. Google is really Googling. Okay, it's 1,000. Okay, but it's not 100. So when someone says infant mortality rate, and they say it as a percentage, you can slap them. Well, don't slap. We can slap them if you want, but I'm not going to stop you. But you can correct them and say infant mortality rate has to be out of 100 to 1,000. So when someone says 7, that's not 7%. That's 0.7% infant mortality rate. Also, to be clear, infant mortality rate is number of deaths out of 1,000 of live births under the age of 1 year. So they died before they were 1. It's considered infant mortality. For just, now you know. At your next really morbid trivia night. So, the lab goes as follows. The first part is actually a k-means part. I'm actually asking you to do k-means on the following variables. Try to create a data visualization, print out the countries in each cluster, kind of like in the Pandora example or in the Iris example. Print out the countries in each cluster and try to see if you can figure out some important variables that would tell you where this country is. Because down here, what I want you to then do is use a decision tree to try to predict infant mortality based on the region that the country is in, the life expectancy for males or females, and the GDP per capita. To see if you can predict infant mortality. Infant mortality is a regression. You can consider it a regression. Then I ask you to try to predict region. What is region? It's like in the drinks, region is Asia, Europe, Africa, America. There's no north and south, it's just America. There's all of it. But try to predict region based on life male, life female, and GDP per capita. And look at the feature importances and see if anything stands out. Was anything like very, very weirdly important for predicting infant mortality? Was any one region very, very important for predicting infant mortality? That's the kind of things I want you to look at. If you really don't want to do the k-means part until later tonight or never, I can't stop you. If you really don't want to do cluster analysis, you want to focus on the trees, by all means. But please work with yourself, work with the person next to you, and this is what I want you to be working on for the next 30 minutes. There's a lot to get done. So, and if you don't finish it, it's good practice for trees and also for cluster analysis. This you can find in the lab folder. Are you using the solutions? Absolutely. But they're not up right now. There are no solutions we can get up right now. But let's get some light. All right, I know. Look to the person next to you and start talking to new friends. The silence is killing me.
Too bright now.
Wake up, yeah. Oops.